So, hi everybody, my name is David. I'm also working in the same organization as Alina and Ollie and other of our team members. So feel free to ask any questions also afterwards, just come by. I'm actually working and based in Austria. Our team is quite geographically separated, and today I want to take a look at native image from a more technical perspective. I'm a developer myself, and I like to talk nerdy things, so sorry for that. Sadly, there won't be any assembly today in my talk. Maybe we can get up on that later. So all of the stuff I'm talking today, of course, might be subject to change, especially since a lot of the stuff I'm talking today actually emerged from a research project, because this entire Graal project was a research project. And I want to take a more technical look at native image, also from a perspective of a compiler person, a systems person, simply for the reason that I do this for a living. So I like compilers, I like complex algorithms and complex technical problems, and I think that native image has the potential to become a real game changer for us, because it would allow us to solve something for which Java has negatively been in the news for quite some time, since its inception initially, namely that it does not have an AOT compiler, and there is this long-going, nearly religious war between AOT compilation and dynamic compilation. I want to reflect on that a little bit. To explain GraalVM, and Alina already did to you, but I like this tweet very, very much, and it's always cool that the community does the documentation for us, and we can use Twitter for that. And I want to highlight one sentence here, and let that sink for a second. That with Graal, we have the first time in the ecosystem of Java, not only user code written in Java itself, but also a compiler written in Java itself. And this has a lot of advantages compared to writing it in C and C++, which is the code base of the hotspot JVM currently. So, going a little bit back in history, or long time back in history when Java was initially released, in the industry, it was considered to be an interpreted language, and this was for a very long time a bad argument against it. People would typically say, if you write Java, it's slower than C, or C++, so if you need something to be very performant, don't use it. Why was that the case initially? If we look at that from a technical perspective, if we have a Java class, and the Java class is loaded by a component you might know or might not know, a little bit of software, a class loader that loads the bytecode. The bytecodes are handed to the interpreter, and the interpreter starts executing those bytecodes one-on-one. And if we look at the interpreter from a technical point of view, it's basically just a big loop over the bytecodes of the class, it fetches bytecode by bytecode, and executes. Of course, it's a little more complex implementation. It's assembly-based, it's a highly optimized interpreter, but still it's an interpreter, which, given that it's not natively compiled, it's slow. That's why, relatively early, a just-in-time compiler, or dynamic compiler, you could also call it, was added to the Java ecosystem, which made the entire picture way more complex than it was initially. Because what we have nowadays in GraalVM, in HotspotVM, also in other virtual machines that do dynamic compilation, is we have this cycle of an interpreter that actually updates, collects profiling information, and this profiling information is later given to a compiler, and the compiler uses it to optimize the code, to produce the fastest possible version of the code. However, the problem, or the advantage actually of Java, it has a very rich class library, it has a lot of tooling, and it has a very object-oriented implementation. So we might end up generating versions of our code, of our machine code at runtime that are not perfectly correct anymore at a certain point in time. We did an optimization that is no longer correct. Best example, we assume the class only has one subclass implementation. Then the user loads another class, we decide the optimization was wrong, so we de-optimize our code back to the interpreter. And this whole thing is, you could call it a very stupid version of machine learning. The virtual machine adapts to your changes, the interpreter will pick up this profiling information, and all of this process continues and continues. Which means for server applications, you reach a very, very good peak performance. Because ideally it stabilizes up to the point that you're actually able in the compiler to optimize the application as much as possible. You have all the dynamic information in there, and that's an advantage compared to AOT compilation. But of course there is the disadvantage that this process takes time. This learning, this adaptation of the system takes a considerable amount of time. However, back then, when Java used to become faster, a lot of customers actually started using it, and the community grew pretty big. And up to the point where we were 2018 and 2019 and 2020, they look similar. If you look at language popularity, benchmark vendors, there are many out there, and they have different statistics behind it. Some use GitHub searches, some use Stack Overflow, some combine it. But in general, Java shows up somewhere at the top. Even though people say since 10 years that Java is dead and nobody wants to use it, and it's a closed language, it's still, for a business use case, a very, very suitable deployment system, which I personally like because I like Java. And then also universities started teaching courses Java around 2000, 2001, and then there was this time where everybody was teaching Java. Now universities migrated, for example, to Python, and think that Python is a more suitable language to learn programming. No matter what, it's still out there and it will remain. In 2011, this whole Graal thing was started with publication of the initial members of the team, which are still all on the team. Actually, our project architect and our leader, Thomas Whitling and Christian Wimmer, a few guys in there, started this idea, why can't we have like one virtual machine that tries to optimize the entire software stack? We have different programming languages, and the reason why we have different programming languages is different languages are better to solve dedicated tasks. You do your statistics, your processing of huge data, probably easier, faster, and less development cycles in R. You do your machine learning in Python, you do your server applications in Java, and you might do your backend server in Node.js or whatever, but it makes sense to have multiple languages. They solve multiple tasks better or worse, so why not compile? However, to this day, what was still missing is an AOT compiler for Java. So actually the capability to skip this entire process of learning a system and have immediate startup. And this was the inception of this native project. If we take a look at warm-up a little bit more in detail, who has heard the term warm-up in here? Hands up. What happens actually in a traditional JVM, if you start executing your application, and I chose a simple standard Java benchmark from the Java couple benchmarks, an old benchmark that has been used in the research community for years. It's just a collection of some sample Java applications, and it perfectly illustrates how the performance of the JVM typically evolves. Here you have runtime in milliseconds per iteration of the workload. Here you have the iterations of the workload, and over time, your performance actually gets better, and your overall runtime decreases. So you take less time per iteration of the workload. And all of this typically starts with the interpreter. In the beginning, you are rather slow compared to the output in the end. Then you start interpreting your application, you have the first compiler, the C1 compiler kick in, and before the Graal virtual machine, you would have the second compiler, the C2 compiler kick in. And then at some point, you reach your final peak performance, and ideally, your peak performance would stay here. But this process can take a considerable amount of time. So you might need 5 to 10 seconds of time. However, what does a normal user typically do? What program do we write first when we try a new programming language? Hello world. So if your hello world takes 1.5 seconds, I mean it doesn't take 1.5 seconds for Java, but think about that, then it's probably not suitable. And hello world is the perfect example because it's so simple. But if you have standalone applications that do not require all of this immense engineering that went into Java to actually reach great peak performance for server-side applications, you still want to have those startups. And Alina gave those micronaut examples already. containers, microservices, anything in the Docker direction is a perfect use case for something. You just spin up something with Java, you give it a certain workload to process, and then it drops out, and all of this just takes 3 seconds, then you don't want to spend 1.5 seconds optimizing for a workload that will be killed after 3 seconds. There's also an advantage in that. However, we need to think about this conceptually, because of course, even though native image is a game changer, it's still not suitable for every application. This is important. You need to reason about the context where it actually may help you. Not all applications require all the engineering and all the optimizations that are in the current JVMs. You have applications that are pretty straightforward. Applications that are CPU bound, for example, by heavy math computation, that don't use 37,000 classes, those applications are not subject to very advanced optimizations, but simply do not require just-in-time compilation. Leopoldseder programs, I talked about them, there is no reason to optimize them that heavily because they will die after 3 seconds. And also not all applications require a JDK. I mean, this has been fixed with JDK 9, but still, if you want to deploy something, and you could even think about this in an embeddability context, if you have some written Java code that is out there and you want to embed it on a microcontroller, then you want the smallest possible footprint. And not even probably the fastest performance, but a deployment scenario that works for you. And also not all applications have terabytes of heaps. A microservice should somehow behave rather nicely, because else it won't be so micro. And all of this actually cries out for AOT compilation. And even though Alina has given some quite big demos, I want to just show you how conceptually easy it is if you have easy applications. So let me just... Oh no. That's not nice. So, I think it also works perfectly. If you just take a recent GraalVM, I just downloaded one a few weeks back, you can go into the GraalVM after you unzip it and you go into the bin file, and then you will find the normal layout you typically have in your JVM. You have a few of the standard executables, you have Java, and all of this stuff. And you have a few more, actually, which said it, let me. And you have a few more, which are, I think we have the, and you have a few more, which we distribute GraalVM. But of course, you have the normal Java running processes in there, and we also have something that is called native image. And you can run that, that's a normal program. And it will tell you to use something, of course. You can look at the help context, it has some markers for stuff, but then you can very easily use it. I should prepare some examples for it. So we just do a hello world program for the sake of simplicity, like that easily as well. You see that not, I think because some small keyboard are not perfect. What do you say?
What's the editor?
Big, among them. So we have our class file now, and instead of navigating back, I will actually just go 2 levels up in my command directory, and I will invoke native image. And we actually have optimizations going on to improve this native image building process itself, so we can actually build it on a dedicated server process that could be remote if you want to use remotely. But for now, I will make it as fast as possible, and I just give it my hello world class. The hello world class contains a main function. And what is happening now, we will go through those.
The class is abstract.
My class is abstract?
Just the class name.
No, sorry. Always something needs to go out. What it does now, it basically just analyzes the application for all the Java code that is inside there. It finds out all the code that is reachable. It takes this code, it tries to optimize it as far as possible. It does some function inlining, and in the end, it gives us, in 23 seconds, a native executable of our hello world, which has 4 megabytes instead of the entire JVM. It does not contain the entire JDK, it just contains those parts of the JDK we are using. Why is it still 4.3 megabytes? What would you think? We're using system out, which is basically half of the JDK. But it's still quite nice. And now if I didn't make a mistake, it should also perfectly execute. You can use command line arguments everything. Should work out of the box. We will talk about some restrictions later. So, let me just switch here. Somewhere on the slides. I want to look so all the slide thing is not so easy. Sorry, they're pre-rendering. So, I talked about the possibility of why it would make sense to AOT compile, and this exactly manages those use cases, match those use cases I didn't talk about. If your startup time matters and your memory footprint matters or embeddability matters, that's the context where you should think of native theme. This does not necessarily mean that it will play nice with your usage of the JDK or your usage of other features, like applications that, we can talk about this later in detail, but applications that, for example, load a lot of code over the wire and then dynamically execute code we have never seen before. This is, of course, technically difficult. But that being said, there are contexts where it makes sense and contexts where it doesn't make sense. If we think about what typically a Java program looks like, it's a few set of types we're using in some configuration files. It's typically a start method if we're going through the normal Java process of calling in via a main function. We have class mark. However, there's also stuff which many people neglect that are typically should be considered part of the Java application, which is the command line arguments you give it, which, trust me, big applications, command line arguments can be a real issue because there can be so many that are given to applications. However, what we always neglect, what is also out there, is the runtime system, and the runtime system typically consists not only of native libraries as a JDK code, but also of large components like the class loader, the GC, and all of this. So, the main technical overview of how this works is basically we're taking all of those things we consider to be part of a Java application, and we try to reach a fixed point in them. We start from our main function, we iterate everything that is reachable, and try to find something we call a closed world. So something that can be safely compiled natively to AOT. Then we take this initial key we produce, we compile all the functions to AOT code, and then we put everything into a native executable. That being said, Windows support is partially there, so we are feature complete on Debian and Linux, and then we run our code. And of course, you can have a trade-off here. If you have, and every Java class typically has, at least generated by the Java C compiler, static initializers, they might be empty, so you're fast. However, a lot of big frameworks have a lot of complex code running in their static initializers. So the question is where and when do you want to execute them? Do you want to execute them at image build time or do you want to execute them at runtime? Some can only be executed at runtime. So those are trade-offs you could need to think about. The analysis that runs in the background that was also part of a few PhDs that went into this project is a points two analysis where we basically start in the main application, look at the object allocations and then follow object allocation per type to all the points that are reachable. And of course, this process requires some memory. So if you have big applications, you need to think about that, you need to actually allocate this initial heap that is initialized at the beginning to AOT compilers. That is simply a requirement to have. There is quite a good application about that. It's also should be linked in our talks. If you're interested in that, how this actually works on a very technical detail. If I say Java performance, which terms pop up in your mind? Benchmark. What else? Memory functions, nice, yes. Garbage collection, yes. I thought about this for some time at home, and I thought, like, what do we teach students actually at university? We typically try to reflect them on what kind of code they wrote. Did they have good complexities? Do they use good data structures? Do they actually use something else than a Java hash map for their work? Or is everything a Java hash map in their code? Of course, we need to reason about the generated code performance, like in which setup am I compiled? Am I interpreted? Which types do I use? All of these kinds of things boiling down to very technical questions. And then we have all the GC performance. That's also important. However, there's also a lot of code out there that actually does not need that much GC, given the fact that it does not do so heavy object allocation. That immensely depends on the setup of your application and the context you're running. Because if we do get this AOT argument further, a lot of the code that is exercised by Java only runs once or twice. Maybe all the code that is run in the startup context. And all of this code is not necessarily important for the performance of the application. Because if it just runs once, it doesn't matter. However, for AOT, we definitely think about size perspective, because code size is very important. We want to have a small footprint. Code size and performance are two dimensions on a very complex, multi-dimensional thingy you need to reason about. Typically, when you apply more optimization, your code size goes up, because more optimization typically means specializing for more dynamic types, which means producing more code. Please don't quote me on that comparison, because this is highly religious, and there have been plain ones going on with us. But I just thought about the different considerations we have when we think about AOT and JIT. Because in a JIT context, we only compile what is actually important. And if code is only run once, we typically don't compile it. It might be that we have a for loop in a function, we have OSR compilations, but else we don't compile. In AOT, we need to compile everything, which is a vastly different requirement, because all the code that potentially runs needs to be compiled. In JIT, we do not care about quotas, because in the end, we probably do a few thousand compilations over the runtime of our JDK, and we don't matter if our code cache has 50 megabytes or 80 megabytes. In an AOT setup, we do matter, because if we deploy an optimization that increases the code size by 20% in every compilation, then we end up with 20% more in the final generated image. And it would not be 4.2 megabytes, but it would be 4.8 megabytes, 60. We typically, in JIT compilation, use profiles and de-optimization for high performance. In an AOT compilation context, we only have one shot at making that right. So it's actually way harder to reach the same level of performance. And that's actually a big comparison factor between native languages like C, C++, and Java. Java is simply written in a way more dynamic way than people write C++ for. And if you go further that route to Scala, Alina mentioned that with why we are performing very well with Graal and Scala, is simply that Scala uses way more types than Java and is way more dynamic and way more abstraction. In an AOT setup, our image sizes matter, and we typically have a rather large deployment footprint in JIT, because before Jigsaw, you would have like a P.jar, the entire JDK, so you amount to something of more than 100 megabytes per default without actually running. Like in AOT, we don't have any one-off at all. Like, ideally, we still do memory allocation. Memory allocators might behave a little bit different, but yeah. However, optimizing AOT for the same performance we have in a JIT compilation context, that's very hard. That's probably, so if you imagine the biggest enterprise server we have out there, and that it typically probably spends like 2 or 3 days warming up until everything is compiled to the point where you reach the ultimate throughput and ultimate peak performance. That's not something you're going to see in a AOT compilation anytime soon. There are ways, and I will talk about them, how we can overcome those problems, but per default, they are not. Remember always this slide is the warm-up, leaving for the rest. We use, when we AOT compile, still the GraalVM compiler, the same compiler that actually compiles your Java code if you're running in a JIT setup, because the compiler is written in Java, so you can actually consume it as a library. very easily you can just say, here you have some bytecode in the machine. That's it. And we apply a lot of optimizations, and a lot of optimizations are also applicable in the dynamic compilation context, in the AOT compilation context. Especially very important optimizations you might have heard about in the Graal context, like partial escape, so getting rid of object allocations. But still, the context is the point we need to think about. Looking at AOT a little bit more, I talked about the futurability point of view already a bit. And I want to shortly outline a bit how that works. It's simplistically, if you really start at main and you iterate instruction per instruction per instruction in your code and try to find out what is used. So I wrote a little function closed world here, a little fast closed world. And our analysis will progress like this is the entry point of your application. That's where you start. That's the first step. The next step is, let's take the first instruction. So we allocate type A. So type A must actually be part of the final heap. So we need to have type A in the final heap. What else do we get with type A? Transitively, automatically. What's the root class of the Java class? Java line object. So this is implicitly immediately part of our AOT-compiled version again. And Java lang object contains a hell of a lot of native functions. So we have suddenly also native code in our final generator. And from there, we do 4 lines of Java code. Those 4 lines of Java code amount to hundreds of types being used. But Java is so, But Java is so expressible and has such a rich class library that we as developers do not think about the, I wouldn't call it technical depth, but the overall complexity we are inherently using every day without actually thinking about the types. Because with these few lines, we basically pulled in half of the GDK universe that is out there. Because there are so many super types, parallel types in the class hierarchy, and that's it. Right. Please don't judge the quality because I didn't talk about that. So, I showed you the slide before, which is point 2, and I've talked a little bit about it, but talking about the heap is actually quite interesting because we can do a lot of optimizations when we talk about the heap. Because typically when we start a Java program, before we execute the first instruction, the main function, the heap should be rather empty-ish. The problem is, as soon as we load a class, we do not even execute any code, we execute static initializers. Static initializers call a lot of crazy stuff. They use native libraries like native calls, J9, what the heck. So there are a lot of objects allocated just for the fact that you blow up the VM, that you start up the VM. You do nothing, you just start it up and load your first application class, but you already have a fair amount of types in your system. And we need to snapshot those types, no matter what. However, there are 2 possible scenarios in our system. Either we execute all those static initializers at build time already, if that's possible. There are some static initializers that need user input, for example, that read from the command line. Then it's hard to execute that at build time because you need the user input at runtime. But if the user input is not necessary, we can have 3 different ways how we run it actually. If you have a normal Java application, you compile the source code, then your classes are loaded, they load configurations and stuff, and then the workloads are out. In a default context, because we mimic Java's behavior, we load classes, but we do not execute the static initializer because that's part of the runtime. However, we also have a scenario where we actually load configuration files and run static initializers at build time if that's possible and configure that. And then you can actually start offloading work to the build time. And we had this one question before about the build times, and that they are so huge. This, of course, depends a lot on what you execute at build time and what you execute at runtime. Because actually executing more at build time gives you better performance at runtime because you don't have to perform the work. But you should still consider that to be a deployment scenario. So building for large applications every time you do your CI job is probably not the right context. There is always this question, what if we use reflection? What if you use class per name? What if you use proxies? And this is a fair and important question because that's such rich feature sets of Java. You use a proxy task and your JVM does runtime code generation of bytecode and compiles to bytecode. And this is problematic because those features are so rich. However, there are solutions to that. You can do that dynamically still, but we need this visible set of possible types. But this is not something we impose on users because we think it's necessary that simply given the fact how this entire system works, there is no other possibility. There is also no possibility in C++ to use something that you have not compiled at the point in time when you deploy it. Of course, you can dynamically link something, but then you know at least the symbols you are dynamically linking. And this is basically the same restriction we have, but this does not mean you cannot use reflection or proxy. You just need to know all the types that might be involved with that future time. And in order to make it for developers as easy as possible, we wrote something we call the tracing agent. It's a Java agent. You just plug it in the system and you run the system with your workloads that you are interested in, and it automatically generates those configuration files. Of course, you might not have tested your system with all the workloads necessary, then you need to iterate with your process. That's sadly possible. Because typically, you test to, or we have had the experience that a lot of people don't fully have all the code coverage with their ready. And that's actually a nice use case because this agent itself is that's used by the JVM API. Because JVM API is a native interface, you can compile your Java application with native image not to be run like Java from a main process, but you can actually export your function APIs as native APIs and use them from C as well. So you can fully actually embed your applications. I talked about, and I think I'm running a bit over time, sorry for that, a bit about performance and about the differences between AOT and JIT compilation and what makes it actually very hard to get there. And this is because a lot of those optimizations employed these days in Java compilers, they require this dynamic information. Because something like inlining, the inlining problem, actually finding out which functions are called in your code to have a broader scope for optimization, heavily depends on the types you use. Imagine an interface like comparable, and the usage of comparable in your containers. There are thousands of types that you can use, but you need to know which types implemented at a particular place in your code so you can actually optimize for the important types. And in native image compiled code, if we run it for Java workloads, I need to mention that for dynamic languages, we also compile the compiler itself, AOT. So if you run JavaScript on top of our system, our compiler will compile itself also to AOT and do dynamic compilation of JavaScript at runtime. But we don't do that for Java because else we would not have this benefit of not having a startup because we then again need to compile at runtime. And a few scenarios still require that you know where dynamic calls go to, which branches are taken, which branches are not taken, and how often a loop is typically executed on it. But there is something which has already been done in the native world we can use for that, which is called PGO, Profile Guided Optimizations. You basically, and I will have a demo for that, but I don't have time, I think. You basically take your application, you instrument it once, run it with the instrumentation code, and the instrumentation code finds out which dynamic types are used, and it gives you a set of profiles that's basically just a big text file, in our case a big binary file, and the next time you build your image, you feed it in those profiles, and then it tries to optimize the routing. You have the same in native applications with GCC or LLVM, you can deploy your optimization. And this solves most of the performance difference between AOT and JIT. Talking about our performance vision for the future, we have these two deployment scenarios that are vastly different, an AOT scenario and a JIT scenario. And if you are dependent on startup memory footprint or packaging size, AOT is definitely the place the direction you want to go if it's possible with the application. The JIT scenario, however, is still at that point in time a scenario that is used for applications that run for decades. So if it's this traditional Java thingy that you have an enterprise server, you spin it up and it runs for 300 days. This is definitely still a JIT deployment use case. However, our goal is to get as far as possible into that direction that you can also do this with an AOT compiled version, because then you can support also the original idea of Java JIT with all the optimizations and beyond. Performance outlook, Alina talked about this a little bit. We're basically working a lot on performance important features, a lot in the direction of memory performance, and since we are officially a product and also have native image in the community edition out in the wild on GitHub, we're also getting a lot of feature requests and a lot of bug issues from the community, and we're constantly improving native image to get there where we want the community wants it to. Try it out yourself. Ideally, you just get GraalVM like I did, take your application, run it, and see what happens. And if it's if it's doing something you do not understand, please open the bug report. But it should ideally work. If you're interested in that, please go to our website. We have an awesome team putting a lot of documentation, a lot of guidelines out there. We have publications, we have tutorials from conferences, and also from user meetups how you can use those tools. And with that, I'm happy to take your questions, and we'll just keep this deployment slides up. Right.
A question about the GC. You mentioned it.
Yes.
I don't remember the exact name of the car, but something here is Scavenger.
We should call it like simple, zero
The
collect.
question is.
I mean, maybe, can I shortly hook in? Maybe to have a clean slate for everybody in the audience. Since we AOT compile the Java code, of course, at runtime we also needed to have a GC. So we actually have a GC implementation ourselves. We compile to AOT code. This is simply required to run Java code.
The question is, if you allow to share this question, you plan to build something from the scratch, something new, and then to do something existing from the Java system to replace this?
Both.
Okay. Fair enough.
Ideally, of course, we always try to reuse as much as possible out there. I mean, the OpenJDK is there; it's an awesome project. But of course, that being said, we are the AOT project, so we actually have like a different object layout of stuff at runtime. So the GC interfaces that are out there and the object layouts, that's not something you just take out in a plug and play and 2 days later it's working. That's fundamental technical difficulties that need to be solved. So it's actually a mixture. Other questions?
Any experience of using in distributed systems like Hadoop, Spark, like what is best?
On Hadoop, Spark, I have not thought of that question actually. I'm a salesperson who don't know of any recent news on that direction. That's a good question.
I think there's something going on Spark, but not something I can basically, comment on.
Okay, then the question is do you have any plan test GraalVM in distributed system? What's the platform you use with Spark to run?
I mean, that depends on how you define the setting up and testing it. So, like what Twitter actually does in production, they have a very complex deployment system. So they spin up machines, they spin up images, they run the compiler in there, so that's very good. And what do you mean dedicated domain?
Yeah, I mean okay, you have a few machines which run a single job, you want to parallelize or distribute. I mean, not in fun, but real.
Yeah, but then it's always the question, do you want the distribution to be automatically happening? Or do you want the user to infer and say, this should be distributed, this should be distributed?
Well, that's actually what we implemented into all this good stuff.
Yeah, that's like the question. If you have a function that distributes your workloads, you could always have one part of the distribution that is capable of being native image compiled. Because in the end, this can be just a call to a remote system, and this remote system can actually be a native AOT compiled version of that problem solution. Because, of course, we support the server stacks, and you can have just a socket connection of nobody ever wants. But that's actually a quite interesting deployment scenario. Other question?
Minor question, how do you resolve instance of in compile time? I saw on the optimization slide there is constant instance of.
for some, yeah, that's like the advantage of this analysis, this points to analysis, this closed world analysis, because imagine an application like Java generics. Everybody knows of type erasure. So we don't have generics at runtime, we just have objects. So when we actually have user code unloading from an array list, we always have type checks that there is actually the type in there that we expect it to be. Imagine an application that just uses array list there with one type. And if you do the analysis, you find out that there is just one type, so you can completely get rid of those checks. Actually, in the analysis, we go far enough, we like remove fields if they're not. Why would you need a field if it's not used? Or methods that are not used? Drop as much as possible, if possible. Any other questions? Okay, thanks a lot. I hope.
There is a small present.